So then we're continuing to focus on circles. Circles are very, very useful to us in a lot of ways. And the rules we're looking at with circles combine with the rules that we've looked at with our isosceles and equilateral triangles in a lot of ways. We have talked about, I have a circle. I have a chord here that happens to be 11 inches long. And I am told that that cuts an arc out here that is, well, let's call it 71-degree arc. If anywhere else on that circle, I have another chord that's 11 inches long, that arc must also be degrees. Or, if I happen to be told that I have an arc 71 degrees, it must cut a chord that is long. Now, it seems kind of like common sense, but there's actually a lot of math that goes into the proof of that we're not going to get into. Not only could it be the same circle, it could actually be another circle. If I label this circle with a radius of r, this circle also has a radius of r. Remember, the only defining features of a circle are its center and its radius. So if two circles have the same radius, they're equivalent. There's nothing different about them other than they're in a different location. So if this circle had a chord the length of 11 inches, that's an arc that is 71 degrees. So what does that 71 degrees mean for that arc? Well, it means that if I drew the radii to the ends of that chord, or to the ends of that arc more specifically, that central angle would be 71 degrees. Or just like we had said before that 71 degrees is 71 3/60ths of a turn, 71 degrees on the arc is 71 3/60ths of the outside of the circle, circumference of the circle. Let's say I have a radius of the circle. I have a chord. From each end of that chord, I can draw in a radius as well. And what I see is that this forms an isosceles triangle. Radii of a circle are all equal to each other. Those two sides, those two red sides are equal. It doesn't matter what the third side is, it's already isosceles. But when we talked about isosceles triangles, sides are equal, this one was. If I draw in an altitude, you remember what else is true about it? So it hits that other side at a right angle, what else does it have to do? Cut what in half? The bottom side. There you go. Yes, it cuts this other side in half. Median. It actually cuts something else in half too. What else? Angle. So it's not only is it a median cutting the opposite side in half, it is also an angle bisector, cutting the angle in half. So that means over here is if that radius that intersects that chord hits it at a right angle, cuts that chord in half, and it cuts this angle in half. work with things. One of the things we're going to work with is V-blocks and stuff like that. Being able to use this idea that any triangle that is made with those radii, we have a chord across the ends of those radius perpendicular to that chord, double talking about it, that a radius hitting that chord at a perpendicular will cut that chord in half and cut the angle in half. It allows us to create right triangles, basically. Can't seem to get my mouth to work. Let's just do an example of it. So let's say I have a chord here that is 54 millimeters long. And I know that it's on a central angle here that is 79 degrees. Let's go 78 degrees. Right now there's no right angles here, so I can't use right triangle trig on it. I can cut it like this, but making that radius perpendicular to the chord turns that into two right triangles. And I now know that this angle has to be how big? Purple.
Oh, 39.
39, there you go, half of the 78. And that this length has to be half of the 84, you got it, 42. Now another interesting property of chords in a circle. Let's say I have a chord like that. I have another chord that's going to come in and hit it like this. And I know that this length here, 3 inches. That's 4 inches. I know that this is 9 inches. If I know that this piece is 3 inches, I know what that piece has to be. The reason is two chords, if they intersect in a circle, break each other into pieces that multiply the same number, the same product. So for this chord, it has pieces of 4 and 9. 6. The other chord has pieces of 3 and x, which has to equal 36. Divided by 3, we get that x has to be 12. It has to be a 12-inch piece. 12 times 3 is 36, 4 times 9 is 36. Those intersecting chords cut each other into pieces that have the same product. But where that gets to be useful is if we combine it with that previous piece. Say I have a circle that I know has a radius 4 inches. Hitting a chord here, get back here. Inches. I want to know what the height of this triangle is. Well, there's actually a couple of different ways we can go about it, but I'm going to do this. I'm going to call this little piece here x. And I know the whole diameter of the circle has to be 8 inches if the radius is. Because I know that that cuts that triangle into 2 3-inch pieces. So that 3 times 3 equals x times 8 minus x. This length here is the diameter minus that x. This will get a little ugly. 3 times 3 is 9. I'll distribute the x. I've got 8x minus x squared. I'm going to subtract 8x from both sides. I'm going to add x squared to both sides. X squared minus 8x plus 9 equals 0. That's a quadratic equation. I can now solve it. Unfortunately, it's not going to be factorable. But the solution always takes on the form of opposite b. So that's a negative 8, so it's going to be a positive 8. Plus or minus the square root of b squared would be negative 8. Minus 4 times a would be the number on the x squared, well, that's just a 1. Times a times c was the number that's by itself, so that's the 9. All over 2 times a, well, a is again the number with the x squared, so that's a 1. This is not something you need to know, by the way, the quadratic formula. That's something to be tested on. Either this is 64, and this is 36. 64 minus 36 is 28. 2 times 1 is just 2, so that's 8 plus or minus the square root of 28. Square root of 28 is 5.29. 8 plus or minus 5.29 over 2. 8 plus 5.29 would be 13.29 over 2. 6.645. 8 minus the 5.29 would be 2.71 over 2 is 1.355. Next, that gives us the two pieces. X is the 1.355. This piece up here is the 6.45. Means that this height is 0.645. Subtract off the 4-inch radius. Now, that's not something I expect you to be able to go and do on your own. That quadratic formula is not something we've learned in this class or last semester. Not something we're responsible for. But it's a little bit of a complex math situation, but it does allow us to really quickly find that. All right. Now, we could find it otherwise. If we didn't know quadratic formula or didn't want to use the quadratic formula, we could have used area to find it. I know that's a triangle that had sides of 4, 6, and 4, right? That's a perimeter. 4 inches plus 6 inches. 14 inches. That's something called a semi-perimeter of 14 inches divided by 2. 7 inches. Looking familiar? Huron's formula. Area is the square root of that semi-perimeter, 7, times the semi-perimeter minus the shortest side, 4. Semi-perimeter minus the next shortest side, which is also 4. Times the semi-perimeter minus the longest side, which is 6. Square root of 7 times 3 times 3 times 6. 19.442 square inches. That's the area of that triangle. But we know that another way to find the area of a triangle, base times height divided by 2. So the base is 6 inches, height, equation. 19.442 times 2 38.884. Still equals the base of 6 times. Then we divide by the 6. $6.481. Slightly different than what we got up here. It's just a round off here. But it's not adding up really good.
That last one is supposed to up in the Hurons.
That's what it is. That's a 1. Thank you. That makes all the difference in the world. Multiplying by 7 is different than multiplying by 1.
No, it's the same.
Telling me that that's wrong is racist.
I didn't say that.
7.937. That's in the recording too. I'm in trouble. 7.937.
Not if we're all laughing. I don't think it counts.
So
Oh, yeah.
7.937 will take that times to 15.875. Then we divide by 6. 2.646. That's much better. Up above we had 2.645. Again, that's round off errors between quadratic formula rounded everything off. Another rule that is extremely important to us talked about lines that are tangent lines. Those tangent lines touch the circle in one spot. Remember the technical definition was every point on the line is outside the circle except for one point that is on the circle. So it touches the circle without going into the circle. Well, if I have a radius of the circle that hits the circle at that same point of tangency, that radius and that tangent have to be perpendicular. Have to form a right angle. This is huge when we combine it with this next piece. If I have another tangent hit the circle up here, obviously it's going to form a right angle with that radius. But now these two tangents intersect outside the circle here. From the point of tangency to where those tangents intersect, on both tangents, that length has to be the same. If I cut it like this, I basically have the isosceles triangle situation. I know that this side is equal to itself. I know the radius is equal to the radius. I have right angles, so I have two sides of right triangles that are the same. The third side has to be the same. That's extremely important for us because we're going to be looking at situations like this. We have round stock sitting in a V block. So we already know two things. If we do the radius out to the edges of that V block, it's going to make a right angle on both sides. And the distance from that point, radius hits the tangent to where the bottom of the V block is, that's going to be the same on both sides. And another rule that results from all of this is if these triangles are the same, this angle here and this angle here has to be the same. And these two angles have to be the same. If I draw a line from the center of the circle to where those two tangents intersect, cuts this angle in half, and it cuts this angle in half. That's going to be very important to us if we're looking at V-block situations. A round stock sitting in a V-block. Let's say we're given that this is a 52-degree block. Cut this up, I know my radius forms a right angle with the sides. I cut this down here, I know that this is 26 degrees. Half of that 52. I now have a right triangle. I know one of the angles. We don't bolt those. We don't. So of course the third angle is pretty easy to find. And hopefully we have at least the radius of the round stock so we can find all the other sides. I think I'm going to take it easy on you today and let you guys, let me just double check what I've got going on. What I have set up in Blackboard for us here. I went and preloaded a bunch of stuff in Blackboard so I don't want to get too far ahead of myself, so I have to redo it all. Yeah, let's leave it at that for now. There's more that's going to come into it. There will be a quiz coming up. Actually, the quiz probably won't be till Monday, but I'll get it posted to work ahead on it if you want to. Right now, there's that new packet from yesterday that was posted. Page 306, problems 9 through 26. Now, on many of these problems, there's more than one thing going on. And we might run into problems that look. I have all sorts of junk going on like this. Try to pick out the parts of the problem that you actually need. If I'm looking for this angle here, what I do, that angle, part of this triangle here that's a right triangle, because that radius has to hit that tangent at a right angle. If I can't solve everything with just that triangle, I might expand to include this triangle. Then I know that these two sides are equal. That might help me out. But all this extra stuff over here, it might be useful for another part of the problem, but it's not useful for finding that single angle there. We will look at some examples actually tomorrow after we do our lecture of a problem where we have stuff just going every direction and how do we break that apart. So for right now, we've got about 18 minutes left to get started on that. I'll let you guys get started working on that, and I'll be here to answer your questions. Those in the room here, did you